Hello everyone, welcome to this lecture number 53 of the NPTEL course on Riemannian geometry. So, starting with this lecture and going to the end of this course, we will discuss how curvature conditions puts restrictions on the topology of your manifold, or turning it around, if your manifold has a certain topology, then you cannot have a Riemannian metric with certain curvature properties. Okay. So, I would like to begin with, so what are basically these curvature conditions? So, this is a basic definition that we will use throughout. So, let M and G be a Riemannian manifold okay. We say that the sectional curvature is bigger than or equal to kappa, and respectively less than equal to kappa or identically equal to kappa if for all p and for all two planes in the tangent space at P, if you look at the corresponding sectional curvature that satisfies this inequality, that is bigger than kappa, and of course respectively less than equal to kappa or is equal to kappa. So, for instance, if the sectional curvature of all two planes is equal to kappa, we say that the sectional curvature is identically equal to kappa. Okay. Alright, so the first theorem that we want to prove on this relationship between curvature conditions and topology is the so called Cartan-Hadamard theorem. Okay. So, what this says is the following. So, let M and G be a complete Riemannian manifold such that the sectional curvature is non-positive. Okay. Then for any p, if you look at the exponential map, so because it is complete, the exponential map is defined on all of the tangent space, this is actually a covering map. Okay. So, in particular what this implies is that if M is simply connected, so in particular what this implies is firstly that if you look at this triple, this is a universal cover, and in fact by uniqueness of universal covers, this is the universal cover up to isomorphism. So, I should replace a with the. So, in other words, the universal cover of M is isomorphic to Rn, because the tangent space is diffeomorphic to Rn, right. Okay. The second point is that this implies that suppose if M is simply connected, then of course it is its own universal cover, right, via the identity map. So then this would imply that M is diffeomorphic to Rn. Okay. So if you just think about this, this is completely I mean this is a beautiful theorem that just by assuming a curvature condition, namely that the sectional curvature is non-positive, you can actually classify the universal cover of your manifold, right. So for instance, if you as an example, if you take something like Sn, so we of course know that there is a standard round metric on Sn which has positive curvature, but you might still wonder that whether it has something with a non-positive curvature also. You know, there are plenty of Riemannian metrics on any given manifold, but what this shows you is that Sn does not admit any complete Riemannian metric. In fact, any Riemannian metric, it is compact, right, so it is automatically complete. So any Riemannian metric with non-positive sectional curvature. Why? Because Sn itself is simply connected, and we know that Sn is not diffeomorphic to Rn, right. I mean, one is compact, the other one is not compact. Okay, so how do you prove this theorem? So there are actually two key ingredients. I will prove one of them and then assume the second one, and then proceed to prove Cartan-Hadamard, and in the next lecture I will actually prove this other ingredient. Okay, so the first ingredient, so I will call it proposition 1, is this little observation due to Ambrose. So this says the following, so let M tilde G tilde and Mg be Riemannian manifolds, okay, and let mu be a local isometry. Okay. So then one key hypothesis, I have forgotten one key hypothesis. Suppose M tilde G tilde is complete, okay. So then the conclusion is that Mg is complete and mu is a smooth cover, is a covering map, okay. So this is the first ingredient that we are going to use. I will prove this in the next lecture. So proof is in the next lecture, okay. Alright, the second key ingredient is this proposition on there being no conjugate points. So the no conjugate points proposition, okay. So this says the following, so let M and G be complete with non-positive sectional curvature, then M has no conjugate points. So i.e. Right, so what this means is that for any geodesic gamma, and any T naught in I. If you look at the set of points that are conjugate to gamma of T naught along gamma, then this is actually empty. So another equivalent way of saying this, or equivalently, and this is actually the way we are going to use this, is that if you look at the exponential map, this is a local diffeo. Why? Because not having conjugate points, remember we had this relationship between conjugate points and the singular values of the exponential map. So not having any conjugate points implies that the derivative of the exponential map at any point is actually invertible. So then by the inverse function theorem, that would imply that the exponential map is a local diffeomorphism, right. Okay, so how do we prove this proposition? Okay, so let gamma be a geodesic. Let P be equal to gamma 0, and let J be any normal Jacobi field. So the goal is to show that if J is non-trivial, then J of L cannot be 0, right. So that would mean that Q cannot or gamma of L cannot be a conjugate point. So let Q be equal to gamma of L. So this will show that gamma of L cannot be a conjugate point, because by definition for it to be a conjugate point there exists a non-trivial Jacobi field that vanishes at the two endpoints, right. So it is enough to show that any such normal non-trivial Jacobi field can never vanish at G of L. Okay, so what is the proof of this? So let me, instead of writing a goal, let me write that this is what I am claiming. Okay, so what is the proof of that? So suppose not, that is there exists a non-trivial Jacobi field such that J of L is actually 0. So then we consider the following function: U of t is the norm squared of J of t. Okay, so let us compute some derivatives. So U is basically the inner product of j comma j. So what will be U prime? There will be 2 times the inner product of j prime comma j, and U double prime will be 2 times the inner product of j double prime j plus 2 times norm j prime squared, okay, just by using the product rule. Alright, but then J is a Jacobi field. So J is a Jacobi field. So J double prime is precisely given by minus Rm of J gamma dot J, okay. But then since J is a normal Jacobi field, by the definition of sectional curvature, so if you go back to the definition of the sectional curvature, this is precisely the norm J squared times the sectional curvature of the plane spanned by J and gamma dot. So notation, I am denoting by J wedge gamma dot the plane spanned by this is a shorthand. this is this is called the wedge product, but I am using it as a shorthand for the plane spanned by J and gamma dot. Okay. So, but then the sectional curvature being non-positive implies that J double prime is non-negative, because there is a negative sign here, right. So, if you go back to our calculation, this implies that U double prime, which was 2 this was incorrect. The inner product of J double prime with J is given by this curvature term, right. So, if you go back to our formula for U double prime, we see that both the terms are now non-negative. So, this is going to be non-negative, okay, or in other words U is a convex function. Okay. So, but then by definition of convexity, for any theta between 0 to 1, U of theta L. So, and any S and T in the interval 0 to L, convexity basically implies that if you take 1 minus theta times S plus theta times T, that the value of U at that point is going to be less than 1 minus theta times U of S plus theta times U of T. So, the typical picture of convex functions is something like this, and then all you are saying is that if you take this secant, then the convex combination of the values of U at this point is going to be bigger. So, this is going to be U of 1 minus theta S plus theta T. So, that is going to be smaller than the convex combination of the values at U of S and U of T. Okay, so, now just apply this with so apply this to maybe S equals 0 and T equals L. So, for any theta, we get that U of theta L is less than equal to 1 minus theta times U of 0 plus theta times U of L, but by assumption, because the Jacobi field vanishes at both 0 and L, both of these are 0. So, this is going to be 0. Okay. On the other hand, we also know that U being the norm squared of something is always non-negative. So, this implies that U of theta L is 0 for all theta in 0 to 1, which just means that for all times T in the interval 0 to L, U of T is 0, okay, or equivalently J is the trivial Jacobi field. So, that is a contradiction, because we assumed that J is not a non-trivial Jacobi field. Okay. So, this completes the proof of our second ingredient. So, now we can prove the Cartan-Hadamard theorem. So, let us prove the Cartan-Hadamard theorem. Okay. So, we consider the exponential map. As I explained previously, proposition 2 implies that exp is a local diffeomorphism. Okay. So, then we do the following, we define a G tilde on TPM by G tilde is the pullback of the Riemannian metric G under the exponential map. Okay, so then because the exponential map is a local diffeomorphism, G tilde is a Riemannian metric on the tangent space. Okay. My claim is that this is in fact a complete metric. So, claim so the tangent space with this new, I mean the tangent space is of course diffeomorphic to Rn. So, you are basically putting this new Riemannian metric on Rn and you are claiming that that's a complete metric space, that's a complete Riemannian manifold. Okay, so before I prove the claim, this basically finishes the proof of Cartan-Hadamard. Why? Because so assuming this, okay, if you look at the exponential map now, by definition this is a local isometry. By how we have defined G tilde, right? Okay. So, then the claim plus the fact that this is a local isometry implies by proposition 1, by this Ambrose's theorem that we have not yet proved, this implies that the exponential map has to be covering. Okay, and that's what is claimed by the Cartan-Hadamard theorem. So, it all boils down to proving this claim. Okay, so let's prove the claim now. So, it relies on the following key observation, that if you have a local isometry, okay, and let us say gamma tilde is a right. So then gamma tilde is a geodesic if and only if you look at the composition, that is a geodesic. So, if and only if which will now go from I to M is a geodesic. Okay, why is this true? This is because of the naturality of the connection. Naturality of the Levi-Civita connection. Okay, so I will leave this. You can go back to our lecture on the Levi-Civita connection, and you can check that the naturality property basically implies this observation. Okay. Okay, so now in order to prove my claim, I make the following subclaim. Okay, so any G tilde geodesic on the tangent space passing through the origin is given simply by the radial line TV. Okay. So it's simply given by gamma tilde of T is TV. Okay, so assuming this again, I will come back to proving the subclaim. All geodesics on TPM with this Riemannian metric passing through this point which is the origin of the tangent space, they exist for all time. But then that's enough by Hopf-Reno. So remember, it's enough to check completeness at a single point, right? So by Hopf-Reno, this was one of the statements in the Hopf-Reno theorem. By Hopf-Reno, this implies that this is a complete Riemannian manifold. Okay, and it proves the claim. All right, so now let us prove the subclaim. So we simply note that if you take the composition of gamma tilde with the exponential map, this by the very definition of the exponential map is a geodesic on M, and because Mg is complete, it exists for all time. But then by the observation, this must imply that the original gamma tilde of T is a geodesic with respect to geodesic on the tangent space, okay, since the exponential map is a local isometry, again by definition of G tilde. Okay. All right, so that completes the proof of the Cartan-Hadamard theorem modulo this key proposition 1 that I stated but did not prove. So in the next lecture we'll give a complete proof of proposition 1, okay, and thereby completing the proof of the Cartan-Hadamard theorem. All right, so that's it for this lecture. Thank you for your attention, and I will see you next time around. Thanks.